Hi everyone. In the previous video, we saw how we can implement stacks using arrays. We discussed the fact that we had this limitation of fixed size. So how we can omit that, in some cases we might not know what should be the stack size, and how we can skip that is by using the linked list implementation, which is you basically have some head pointer. We have already discussed linked list. That's pointing to the beginning of the list, and each node connects to the other one. So let's try to see how it will conceptually work. So in this case, I have an empty list where head will be actually equal to null in the beginning. Okay, so I'm going to remove this just to avoid confusion. Now, if we do something like push 5, what how this stack implementation should behave is it should create a new node with the value 5. Head should now point to this new node, and this new node's next should be null, which is now head no longer points to null. Now let's try to do another push, which is like if we have push 6, what it will do is again it will create a new node 6 with the value 6 and this value right now pointing to null. But how we are going to fix that is, since this head, we are going to insert this node in the beginning of the list, which is right here. So now head starts pointing to the new node that's just created, and this new node's next, which is this one, points to the original head or this particular value. And a singly, like we are implementing the stack in the form of a singly linked list with just the head pointer, because we don't need the tail here. The head is actually in, like when we compare it to the stack ADT, it's just the top, because what we are trying to do is like whichever element we are pushing in the end, that's the first element where the top is pointing to. So let me draw it once again, like in a more clear way. So let's say our initial head is null. Okay, so now what I'm going to do is I'm going to push the value 5. So we are going to create a new node 5, and now head starts pointing, like since the head is empty, or like let's, instead of starting to call this head, let's call this the top. So like top and head both are the same things. So whenever we try to insert a new node, and if the top is null, we are just going to point the top to this new node, which is now it's 5. Next, if we try to do something like push 6, we are going to insert a new node with the value 6 in the beginning of the list, which is now this 6 starts pointing to the top variable, which is we have the 6, and now it starts pointing to the top variable, which is in this case 5. And then we are going to increment the top pointer by, like we'll relocate the top pointer to start pointing to the new node that we just inserted. Again, the API provided by the linked list is exactly the same, which is the push, pop, empty, as well as the size and the peak operation. And how we can define that in the form of classes is, now instead of having an array, we now have a class called stack underscore ll. Now this has a private variable, and we have already covered this node class. Like you can have it as an inner class, or you can have it as a separate struct. If you don't know the node class, go back to the linked list lecture. So now it will have a node star next that points to the next element, as well as the int data that will store the data. There's going to be a third variable. You remember in the previous video we saw there was a top variable uh, that was pointing to the index of the recent element in the stack. In this case, we have, instead of head, we just have this node star top, and then we can implement these functions. It's like pretty straightforward. I won't go into details because it's like very simple. You should know these, all these functions, like is empty, pop, push, like for both stacks as well as arrays, which is like implementation of stacks through arrays or linked lists. Next, what we are going to see is now that, like, we know, like, if we are trying to insert a new node in the first position in a linked list, the operation just takes O of one. So basically, uh, earlier we had this issue that it was fixed, the size was kind of fixed for arrays. Now we have removed that issue because linked lists don't have any size. We can just keep on adding more nodes at the end of this list, or basically we are adding it to the front of the list, but it still takes constant amount of time. So the trade-off now is we are now storing an additional node pointer, so we are consuming more memory. So let's see the characteristics as well as operations of this implementation, which is, again, now we have a new flexible size instead of a fixed size. We can store similar elements in this linked list, and we access through the top pointer instead of an index. The operations are very similar to what we saw. It's exactly the same. We have the push, pop, peek, size, and is empty. Now let's talk about the performance. It's going to be O of 1 for all cases. Like whenever we are trying to push an element in the list, you can see that I'm just like adding some element to the top node and manipulating some pointers. If you are trying to remove an element, what we can do is we can just state top is equal to tops next, because, and then delete this, the original top variable. So basically, if top starts pointing to this, we have removed the topmost element on the stack. So that's why the pop will be again operation. The time for the pop operation will be again O of 1. Similarly, for peak, size, and is empty, we can find like is empty is just like if top is equal to null or not. Size, we can again keep a variable for size, and whenever we are adding, we can add that. And the last one was peak, which is again like what is top pointing to. Like if we just return tops data, that is basically the peak. So what's the benefit of this approach? Again, like it's taking constant time for all the operations. And now we also have a variable size, which is we can add any numbers. The drawbacks is like we are now consuming more memory because we are now storing the pointers. And now we are going to see how stacks can be implemented in C++. I'm going to show that in a new video because it's a, a different concept. So we're going to see in the next video.